This is a GCSE revision video on logic gates. Now the first thing that you need to know about logic gates is that there are two types of electronic signal. One of them is analog and one of them is digital. Now analog can have any value, so it can be anywhere between 0, let's say that this is the 0 mark here. It can be anywhere between 0 and let's say that's, for example, 12 volts. It can also be 11.5 or 10.5 or 9.5 or 8.62 or any value between the maximum and the minimum. Digital can only be two things. It can either be on, which we call 1, or off, which we call 0. So analog and digital are two different types of electrical signal. Analog can be any value, digital is just either on or off. Now, as you probably know, computers mostly use digital signals to communicate, and that's what logic gates use as well. The digital is either on or off, and logic gates deal with things either being on or being off. Now, the most simple type of logic gate is called a NOT gate. A NOT gate in your circuit diagram would look like this. Okay, and the NOT gate is a triangle with a circle there, and what the NOT gate does is if there is a signal of a 1 coming in, it puts out a signal of a 0. And if there is a signal of a 0 coming in, it puts out a signal of a 1. So basically, logic gates do what they say in the name. So a NOT gate gives an output, input. A NOT gate gives an output of the opposite of the input. It is not the same as the input. So if its input is 1, the output is 0, and if the input is 0, the output is 1. Now what I've done here is I've drawn a table of almost like results for the NOT gate, and we call that a truth table. And the truth table tells you what inputs give what outputs for that particular logic gate. So the NOT gate, the most simple one, triangle with a circle, just does the opposite of what the input is. Now things get slightly more complicated when you have two inputs. So the next gate we're going to look at is an AND gate. Now two inputs for an AND gate looks like a big letter D, like that. Two inputs give one output, and as you can probably guess from the name, the AND gate looks at both of these inputs and says, well, if this one and this one are 1, then this one will also be 1. So if we have A and B, the truth table, if we have the output there, the truth table will look something like this. So when you've got 0 and 0 coming in with A and B, your output will be 0, 0 and 1. This one and this one are not on, so that's still a 0. 1 and 0, this one and this one are still not on, so that's a 0. But when 1 and 1, the output is 1 because A and B are on already. So that's the AND gate. There's a slightly different variation of the AND gate, which is called the NAND gate. A NAND gate is basically short for not AND. So a NAND gate does the exact opposite of an AND gate, and when A and B are not both on, then the output is 1. Now the difference with a NAND gate is it's got a little circle there. That circle in a logic gate means not, means the opposite of whatever the one without the circle is. So this is a NAND gate, and we've got the same thing here for the truth table. except this time it gives the opposite output. So that's 1, 1, 1, 0. So only when these are not both on, they're not this one and this one, will it give a positive output. Sometimes you want to take two signals, and if one of them is on, you want to say, okay, just one of these is on, and we'll give an output for that. And for that, we would use an OR gate. Now you can probably work out again from the name that an OR gate has two inputs. It looks a little bit like a spaceship, like that. It has two inputs, A and B, and if A or B are on, then it gives a positive output. So A, B, out, 0, 0, 0, 1, 1, 0, 1, 1. A or B are off in here, so that's an output of 0. Here, A or B, yeah, on, 1, A or B, yeah, and here, A or B, yeah, they're both on, so that's a 1 as well. So the OR gate gives an output, a positive output, a 1 for the output, if A or B or both are on. Now, same with the ANDs. The NOR gate does the opposite. And same with the ANDs again. The gate looks the same, except it's got a little circle for the NOT. And then, so the NOT OR gate gives a truth table of the opposite of the OR gate. So only when A or B are not on will it give a positive output. 0, 0, and 1. So to summarize, logic gates control the output based on what the inputs are, and it makes a decision based on that. So the AND gate looks for both A and B being on. The not AND gate, the NAND gate, looks for A and B both being on, and that gives a negative output, the opposite of the AND gate. The OR gate is this one, and that looks for either A or B being on and gives a positive output. And the NOR gate does the opposite, it looks for A or B being on and gives a 0 or a negative output. So those are the logic gates, along with the simple NOT gate here, just does the opposite of whatever the input is. And those are used frequently in computers. Now, one thing that you might have to do for your exam is combine those gates. So, here I've drawn two example circuits. So we'll look at the top one first. The top one is a system for a fire detection and safety system. So you've got a heat sensor and a smoke sensor. They're going through to an OR gate. So when the heat sensor or the smoke sensor detect anything, then one of these signals is going to be positive. If the heat sensor detects something, a temperature that's too high, then this will be positive. It'll be a 1, and if the smoke sensor senses smoke, this will be a 1. So either of those create a positive output. The positive output would switch a relay. Remember, a relay is an electromagnetic switch, and that switch would turn on a sprinkler system. This one lower down is a little bit more complicated. It's a heat sensor and a light sensor. They each go through a NOT gate. So that reverses the signal. So if this is a 1, then this is a 0, or if this is a 0, then this is a 1. So when this heats up, the signal being given out here is a 1, and so this signal coming out here is a 0. Same with the light sensor. When it's bright light, this signal is a 1, this signal coming out here is a 0. But when it cools down, then this becomes a 0, and when it gets dark, this becomes a 0. Both of these become 1s, and they go through to this AND gate, which is looking for this and this being 1s. That switches a relay. the relay turns on the heater. When this is 1, then this is 1. So this system could be used to switch on a heater at night when it is cold. So when it's dark and cold, the heater turns on. So these are 2 examples of how you could use some of these logic gates in circuits, and that is something that you may have to do in an exam.